In this video, we learn about implicit differentiation. Now, implicit differentiation is a method for differentiating functions in which y is implicitly defined. What we mean by that is functions or expressions looking like x squared plus y squared equals to 4, or sine of y minus 2xy equals to x squared, or even 3 square root of y plus x squared y plus y equals to 7 sine of x. Now, the key difference in these expressions or functions compared to what we've seen so far is that in this case, we don't have an expression looking like y equals to f of x or y is equal to some function of x. No, in this case, y is implicitly defined. Looking at the first one, x squared plus y squared equals to 4. Looking at that, we can't say right away what y is equal to. No, it's implicit. So, the way we differentiate these is using implicit differentiation, and the method for that can be summarized as follows. The key thing to keep in mind is that y is just a function of x, and it should always be treated as such. In other words, we can think of y as being y of x, because it is just a function of x, like g of x, h of x, and so on. Once we have that in mind, all the other techniques we've seen so far will still work. Things like the power rule, the product rule, the quotient rule, or the chain rule, they still work, so we're fine there. Now, for example, we may be asked to differentiate 2xy equals to sine of y. And the key thing to see here is that if we replace y by y of x, in other words, we just rewrite it that way, then it becomes quite apparent that on the left-hand side, we're looking at the product of two functions, 2x and y of x. On the right-hand side, we're dealing with a composite function, sine of y of x. And so to differentiate this, on the left-hand side, we'll need to use the product rule, whereas on the right-hand side, we'll need to use the chain rule. And we'll see far more about this in just a minute, but the answer to differentiate that expression would be 2 times y of x plus 2x dy dx equals to dy dx cosine of y. And that stems from the product rule on the left-hand side and the chain rule on the right-hand side. Now, enough of this slideshow. Let's actually work our way through a few examples with handwritten notes. Okay, let's see how to differentiate using implicit differentiation with a few examples. Now, the first one we're given 2xy equals to 3x squared, and we're asked to 1. Differentiate with respect to x, and 2. To find dy dx, the derivative of y. Now, to do this, the first thing we need to notice is when we write 2xy equals to 3x squared, the left-hand side here should be thought of as the product of two functions. In other words, we need to think of 2xy as u of x times v of x, where u of x equals to 2x and v of x is equal to y. And in fact, this is very important. We need to always keep in mind that y should be thought of as y of x. It's a function of x, like f of x or g of x or h of x. So each time we see y in this kind of expression, we need to be thinking that it's a function of x. Now, if u of x equals to 2x, then u dash of x is equal to 2. If v of x is equal to y, then v dash of x will be equal to dy dx. And now that we've done this, to differentiate 2xy, we just use the product rule. And the product rule, remember, tells us that if we have the product of two functions uv, the derivative is u dash v plus uv dash. So in this case, that would be u dash v is 2y plus uv dash, so that's 2x times dy dx. And that's the left-hand side done. On the right-hand side, the derivative of 3x squared, well, that's just 6x. And in fact, we can go a little further. We can simplify everything by dividing throughout by 2, which leads us to y plus x dy dx is equal to 3x. And that's that. We've just differentiated this expression using implicit differentiation. So I'll just box that result there. Now for the second question, that was question 1, The second question was to find dy dx. And in fact, that's quite simple. All we need to do is rearrange the expression we just found and boxed to make dy dx the subject. And we do this as follows. Subtracting y from each side leads us to x times dy dx equals to 3x minus y. And finally, dividing both sides by x leads us to dy dx equals to 3x minus y over x. And there we have it. We have the expression for the derivative dy dx. The second example we're given, we're asked to differentiate with respect to x again, the expression sine of y equals to 4x. Now to begin with, let's just rewrite this, replacing y by y of x, as follows. That sine of y of x equals to 4x. Now the reason why we do this is this really highlights the fact that y should be treated as a function of x, and now we can see quite clearly that on the left-hand side we're dealing with a composite function, that sine of y of x. And to differentiate composite functions we need to use the chain rule. One of the two formula, or one of the two ways we saw to write the formula for the chain rule is as follows. F of x, or if f of x, equals to g of h of x, a composite function, then the derivative f dash of x will equal to h dash of x times g dash of h of x. So that's the formula we're going to use here. Make a note of it if you haven't seen it before. Now, comparing that, the g of h of x, to the expression we have, sine of y of x would be the inner function, h of x, and the outer function would be sine. So we have g, that would be the sine of h of x. Now we can see with our formula that the derivative of that is h dash of x times g dash of h of x. So in this case that would be y dash of x times the derivative of sine, which would be cosine, of y of x. And that should equal to the derivative of the right-hand side. And the derivative of 4x is just 4. And we're done. We've just differentiated this expression with respect to x. Now we can of course rewrite this in terms of dy dx and y, and that would be dy dx times cosine of y, and that equals to 4. And there we have it. We've just differentiated this expression with respect to x using implicit differentiation. Let's look at a couple more examples. Okay, now in this next example we're asked to differentiate with respect to x, y squared minus 2y equals to 3x squared. And just as we did previously, the first thing we're going to do here is rewrite this expression, replacing every y by y of x. And that's just to remind us that y is a function of x. So that would look like this. That would be y of x, in parentheses squared, minus 2y of x equals to 3x squared. And now that we've done this, it's quite clear that we're dealing with a composite function here. When we look at y of x squared, we can think of that again as g of h of x. And remember, we saw that using the chain rule, when we differentiate this, if I call this f of x, when we differentiate this, we get f dash of x equals to h dash of x times g dash of h of x. Now, keeping that in mind, and comparing it to what we have here on the left in blue, the inner function in this case, y of x, would be h of x, and the square function would be g. So we have g of h of x there. Now we can differentiate using the chain rule. So we'd have h dash of x, that would be in this case y dash of x, times g dash of h of x. So that would be the derivative of x squared, or of the square function, so that would be 2 times y of x. minus 2 times the derivative of y of x, so that's just 2y dash of x, equals to the derivative of 3x squared, and that's 6x. And of course we can rewrite this in terms of dy dx, so that would be dy dx times 2 times y minus 2 dy dx equals to 6x. And we can see here that all of the terms have a common factor, which is 2. So let's get rid of that. We divide throughout by 2, leading us to the answer y dy dx minus dy dx equals to 3x. And there we have it. We've just differentiated this expression with respect to x using implicit differentiation. Now, for the last example, we're asked to differentiate with respect to x, xy equals to the square root of y. Now, just as we did before, the first thing we're going to do here is to rewrite this, replacing every y we see by y of x. So that would be x times y of x equals to the square root of y of x. Now, we can quite clearly see that on the left-hand side we're dealing with a product of two functions, that's x times y of x, and so we can think of that as u of x times v of x, where u of x equals to x and v of x equals to y of x. And so u dash of x, the derivative, would equal to 1, and v dash of x, well, that would just be y dash of x. And so we'll be able to use the product rule here to differentiate the left-hand side. And so doing that leads us to u dash v plus uv dash. That would be 1 times y of x, that's just y of x, plus uv dash, so that would be x times y dash of x. So x times y dash of x equals to the derivative of the right-hand side. Now, looking at the right-hand side, we can see that we're dealing with a composite function again. Indeed, we have square root of y of x. So we're going to need to use this formula here again for the chain rule. But now, let's just remind ourselves of the derivative of the square root function. Now, if you don't know this off by heart, it's worth knowing. It comes up a lot. Just remember that if we have square root of x, the derivative equals to 1 over 2 times the square root of x. And sure, we could find that with the power rule for differentiation, but as I said, the square root function comes up so much in exam questions, it's really worth knowing that result off by heart. Okay, now back to the right-hand side here. Comparing it to this, g of h of x, we have square root of y of x. So y of x would be the h of x, and the square root function outside of that would be the g, so that's g of h of x. Now, to differentiate that, we just use the chain rule, which tells us that the derivative should be equal to h dash of x, so that's y dash of x, times g dash of h of x. And so using this formula we just saw here, we can find our g dash, so that's 1 over 2 times the square root of y of x. And we're done. We've just differentiated this expression. And we can of course rewrite this in terms of dy dx and y, and that would look like follows. That would be y plus x dy dx equals to dy dx times 1 over 2 square root of y. And there we have it. That's how we differentiate using implicit differentiation.